Good evening, ladies and gentlemen. I'm Philippe Blondeel from the Department of Computer Science at the KU Leuven. I will be presenting to you a talk about prerefined multi-level Quasi-Monte Carlo for Galerkin finite element methods with applications in geotechnical engineering. So this work was co-authored together with colleagues from the Department of Computer Science, Pieter Jan Robbe and Stefan van der Wallen, also with colleagues from the Department of Civil Engineering, Saint-François and Geert Lombard. So let's dive right in, shall we? So this is the outline of the presentation. So I'll give an introduction. So it's a bit of setting the stage for P multi-level Quasi-Monte Carlo and what's to come. Afterwards, I'll talk a bit more about the method itself before moving on to uncertainty modeling. This will be an important part of the presentation. Then we'll move on to benchmarking and results, where I'll show you some results. And at last, conclusion and outlook. So, prerefined multi-level Monte Carlo. So this is a novel algorithm that we developed, and it considerably speeds up the computation of statistics of a quantity of interest derived from the solution of a model described by a partial differential equation with random coefficients. So this will be benchmarked against standard multi-level Monte Carlo and standard multi-level Quasi-Monte Carlo. So the problem on which we will benchmark it is actually a geotechnical engineering problem, so it's a nonlinear slope stability problem. So here this is the case itself. So the problem is to assess the stability of man-made or natural slopes. So as you can see on the picture, this is an excavation. So major excavation works are typically done when you need to build foundations for a house, for skyscrapers, or for other civil constructions. So as you can imagine, so you don't want this slope that you've dug out to collapse on itself and void all the work you've accomplished in the previous days. So this is actually the problem that I will focus on. This is the case that we will consider. So we need to assess the stability of these slopes. It's a nonlinear problem, and the uncertainty is located in the source cohesion. So the model is a two-dimensional problem, and we use plane strain, which means that in the z direction it's infinite depth. So P multi-level Quasi-Monte Carlo, what is the novelty is that it uses a hierarchy of higher order finite elements instead of the more classical H refinement, which just consists of refining the resolution of the mesh, so by increasing the number of elements in the mesh. So this is then combined with QMC sample points. Because we use the hierarchy based on higher order finite elements, we cannot just simply assign randomness to the whole element. So the randomness will be modeled by means of a random field. So the discrete values of this random field, we cannot just simply assign one value from this random field to the whole element, because as you imagine, as you see, the number of elements across the level stays the same. We just increase the polynomial order of the finite element itself for our mesh hierarchy. So what we need to do, we need to decouple. Here we will decouple the relation between the resolution of the random field and the resolution of the mesh, because we're not refining the mesh in an H way, but we still want a refinement of the resolution of the random field. So we will need to decouple those two, and this will be a major point of talk in this presentation. So we will need to give careful consideration of the generation of the random field over successive levels, where, in which points we generate discrete values, and how to incorporate them into the model. So now you just go back to a bit of the basics. So the expected value for multi-level Monte Carlo and multi-level Quasi-Monte Carlo. So the idea of these multi-level methods is to take many computational cheap samples on coarse meshes and a few computational expensive samples on fine meshes. So the first part of the equation, so the 1 over n0 sum p0, so this is the expected value on a very coarse mesh plus a sum term, so these are corrections of differences. So you actually correct it by computing differences over the different levels. for multilevel Quasi-Monte Carlo on the second equation, you see there is a blue term being added. This relates to the number of shifts, random shifts that you need in order to recover adequate computation of the variances, because with Quasi-Monte Carlo you're dealing with deterministic sample points. So in order to introduce some sort of randomness in it, you use these random shifts. So these are these QMC points. So you will use rank 1 lattice rules as specified in the work of Nuyens et al. So on the left side the figure, it's a unit square 0 and 1, 0, 1 with Monte Carlo points, so at random in space. While on the right side it's Quasi-Monte Carlo points. You see it's space filling. So you can distinguish 3 colors, green, red and blue. So the sets of green points is not shifted. The red points are then shifted once and the blue points are shifted again. So this introduced the randomness. I won't go into more details about this shifting, which can be found in literature. So below you see the representation of the QMC points as an open lattice rule. So open lattice rules means that we can add more points to our already existing Quasi-Monte Carlo points on the fly. So you don't need to know the total number of points in advance. So let's move on to the finite element formulation. So a partial differential equation can be discretized by means of the variational formula in the following algebraic form. So k times u times f. F is a vector, the force vector, u is the displacement vector, and k is the global stiffness matrix. So you have to solve this. But the global stiffness matrix, it results from the assembly of the element stiffness matrices, like I put below. So Ke is an integral over the elements domain of the matrix B, which contains a derivative of the element shape functions times an element times D, the elastoplastic constitutive matrix. In our case, the uncertainty will be located in this elastoplastic constitutive matrix. Because we're in the elastoplastic domain, this matrix is computed by an elastic predictor, plastic corrector. I won't say any more about it. This can also be found back in literature. The most important thing to know is that the uncertainty is located in this matrix D. This multiplication of matrices is then numerically integrated by means of Gauss quadrature. This is also important. Numerically integrated, we will come back to it, because this will be how the uncertainty is incorporated into our finite element model. So here we show the mesh hierarchy for standard multilevel Quasi-Monte Carlo, also referred to as H multilevel Quasi-Monte Carlo. So it makes use of a mesh hierarchy based on nested geometric refinement. As you can see, you just refine the mesh element-wise. For a p multilevel Quasi-Monte Carlo method, we increase the element's polynomial order. So which means that we increase the number of nodes per element and the number of shape functions, so that we can model, or you can represent, higher order displacements inside the element itself. So quartic, quadratic, cubic, quartic, quintic, etc. So this is our mesh hierarchy that will be used for p multilevel Quasi-Monte Carlo. So now we move on to uncertainty modeling, the random fields. So I said before, the uncertain material parameter consists of the Soul's cohesion. It is spatially varying, and we're going to represent this by means of a random field. So then I'll give an ad hoc definition of a random field. It's a collection of random variables at certain discrete locations. It's also important to bear in mind that certain discrete locations that can be chosen by the user. So there are many different techniques to do this. So you can do a QR decomposition, a spectral decomposition, a circulant embedding, or a Karune-Leuven expansion. And we will focus and use the Karune-Leuven expansion. So this is the representation of a Karune-Leuven expansion. So how do we construct these random fields? It's in two parts. First, we construct a Gaussian random field by means of a Karune-Leuven expansion, as written here. So it's zx omega, so in certain points, x, omega is the randomness, equals the z, so this is the mean of the field, plus a summation term which encompasses eigenvalues, eigenvectors, and standard normally distributed random variables. The eigenvalues and eigenvectors can be obtained by solving a Fredholm integral equation given a covariance kernel. In our case, we will use a Matern covariance kernel. That's everything I will say about this. This can be found back in the literature if you're interested in more details, or you can contact me and I will be happy to give more explanations. Second part is to transform this Gaussian random field to a log normal random field by applying the exponential pointwise to every point contained in the matrix Z. So this right below, because we cannot use just a Gaussian random field, because it can have negative values, and you can imagine negative values for source cohesion. It's nonsensical, non-physical. So we know how to generate our random field by means of Caron-Leuven. Now how we're going to incorporate this into the model. So classically, this is done by means of the midpoint approach. So each element is assigned one value of the random field. This means that the size of the mesh equals the size of the random field. So you have as many elements as you have discrete values in your random field. If you refine your mesh, you will automatically have to refine your random field. p-MLQMC makes use of the integration point method. So each quadrature point, like as you remember, like I talked before, the element stiffness matrix is an integral which is integrated numerically by means of Gaussian quadrature. So each quadrature point is assigned one value of the random field. So the resolution of your random field is it's bigger than the resolution of your mesh. You have more discrete values of your random field than you have number of elements. And now we'll go into detail. I will explain how you generate, or where you have to generate instances of this random field. So we distinguish three different approaches. We have the non-nested approach, the global nested approach, and the local nested approach. Why do we actually bother with these approaches? So the idea is we need to have good correlation between successive levels of the random fields. If we have this, then the finite element solutions will also be nicely correlated. This will lead to a good decrease of the variance of the difference of a quantity of interest, which will lead to a lower number of samples per level and a lower computational cost. So as you will see in the results, it's very important to make the right decision. So this is just setting the stage, the convention I will use. So I will show it to you on a reference triangular finite element where the locations where the instances of the random fields need to be generated are located. So the red squares are the location of the discrete values of the random field, where you will generate the instances of the random field. Excuse me. And the triangles are the quadrature points. So the non-nested approach, naively, this is the most naive approach, the idea is to use the location of the quadrature points on each level as a location of the discrete values of the random field. So as you can see, for each level, you will generate instances of the random field in the locations of the quadrature points. So the red squares and the blue triangles coincide for each level. The advantage, it's easily extensible, so an extra level can easily be added. The disadvantages, which will lead to a very high computational cost due to the very slow decrease of the variance of the difference. A different approach is the global nested approach. So the idea is to start from a user-defined maximum level capital L. So this is the maximum level that your simulation, multi-level simulation, can reach. If you need one more level, then you have to restart it with a new hierarchy. So on this maximal level L, that level, you compute the discrete values of the random field in the locations of the quadrature points. For coarser fields, so I give the example with level 3 being a maximal level, there the locations where you will compute instances of your random field equal the location of the quadrature points. For coarser levels, so level 2, 1, 0, you compute subsets of these locations, so of the red circles, such that for each level, so for level 2 for example, these red circles are closest to the actual quadrature points. And then during the numerical integration, you integrate with the D matrix with the uncertainty corresponding to the closest quadrature point. That's the idea. So the advantage is this will lead to the good degrees of the variance of your differences, but your maximum number of levels is fixed. So you cannot easily add another level if you need one. So if you have 3 levels maximum and you need a 4th, you cannot reuse the previous computed samples and information because you will use different points, so their adaptability for extra levels is not there. An idea would be to choose a high enough level so you don't run into this problem. Another approach is the local nested approach. Instead of starting from the finest level, so a maximum L, and then computing subsets for all the coarser levels, you compute it 2 by 2. So here I give an example level 1 and level 0, level 2 and level 1. So if you need samples on level 1, you will also need the differences, so the coarser level 0, level 0. For level 1, you will generate discrete values of the random field in your quadrature points, and for the coarser level, you will compute a subset of these locations such that they are closest to the quadrature points of that level. So I give the example with level 1 and 0 and level 2 and 1. So you can easily add another level if needed. This slightly increases the complexity of the code, but it's a minor disadvantage. So let's move on to benchmarking and result. So the quantity of interest needs to be chosen, and we choose a vertical displacement of the node located at the upper left corner, as you can see in the picture. We then can compute uncertainty on the solution. So here we show the absolute value of the deflection of that point, in function of the percentage of the slope's own weight. And as you can see, so the blue is actually like the uncertainty, the confidence interval, while the orange is the mean and the dotted orange is the 1 sigma bound. So we're clearly in the plastic domain, as you can see, because it's not straight, it's curved. Now I will show you the benchmarking, so a comparison between a global nested approach and a non-nested approach. So as you can see, in orange it's the non-nested approach, and in blue it's the global nested approach for a total number of 4 levels, 0, 1, 2, 3, with an order, so the refinement, the order of the elements is 1, 3, 5, 7, as you can see in the table. So you see the runtime of the non-nested approach is much higher than of the global nested approach, and the origin of this higher runtime can be found in the variance of the differences. So this difference, the variance of difference, decreases faster or decreases better when you use this nested approach and when you use this non-nested approach. This is due to the correlation of these fields and the correlation of the finite element solution. So here we can conclude that the global nested approach performs better than the non-nested approach. So unfortunately I cannot show you results for the local nested approach due to unforeseen circumstances with the supercomputer here in Leuven. So having decided that the global nested approach is the best if you compare it with a non-nested approach, I will now make the comparison between the classical standard multi-level Monte Carlo, so p-MLQMC, HMLC, and p-refined multi-level Monte Carlo. So the blue line is of course our new results, and as you can see it outperforms the red line with the open circles, which tops at 156 hours for a given tolerance. This is H multi-level Monte Carlo, in comparisons with our new method, p-multi-level Quasi-Monte Carlo, which tops around 3 hours. So you have a speed up of a factor of 44 in favor of our p-refined multi-level Quasi-Monte Carlo. If you make the comparison between our method and p-multilevel Monte Carlo, you see that p-multilevel Quasi-Monte Carlo outperforms p-MLMC by a factor 3 because of this QMC sample point. So our method is a factor 44 faster than standard multi-level Monte Carlo. Here I show it to you with more levels, so we have chosen a total of 9 levels, so 0, 1, 2, 3, 4, 5 until 8, with order going from 1 to 9. And as you see, the decrease for a global nested approach, p-multilevel Monte Carlo, the runtime, the cost is equivalent to 1 over epsilon, so epsilon being the tolerance that you want. Variances decrease, variance of the difference decreases nicely, and your samples also decrease nicely, so you have most of your samples on the coarser level and decreasing amount on finer levels. So this is what you want. So now we can look for a conclusion and look to the future. So we can conclude that with p-MLQMC we have a speed up of a factor 44 if you compare with standard multi-level Monte Carlo, which is quite a high number. Our global nested approach outperforms our non-nested approach, and I've put here global nested and local nested because local nested is similar. It will also outperform non-nested, and I expect even that it will slightly outperform global nested. I haven't seen results for it, so I cannot make this a hard conclusion. The outlook, so extending p-MLQMC for 3-dimensional problems. So this is currently ongoing. This is working quite good. So we're using higher order finite element based on higher hierarchical shape functions. So here we've used standard shape functions, standard higher order shape functions with hierarchical higher order shape functions. This means that all your shape functions from order 1 are included in order 2, and these ones are included in order 3, in order 4, etc. So if you then combine this with a nested quadrature points over the level, based for example on nested sparse grids, there is a possibility of reusing finite elements or information over the levels, which will then be the B matrix that can be reused, and you can have an even bigger speed up. You can win more than without using it. So there is even a factor more that you can win by this approach. Then future-wise, we'll convert it to multi-index Monte Carlo so that you adaptively refine in P and H at the same time. This is the next step, and we'll also use higher order digital nets instead of rank 1 lattice rule for the generation of your QMC points. We suspect that there's also a gain to be found there. So these are the references. Most of the results pertaining to the global nested approach have been published already in a paper from a couple of months ago, and then the previous information comparisons have been published in proceedings. So this concludes my presentation. I want to thank you for your attention. If you have any questions pertaining to p-multilevel Quasi-Monte Carlo, how to incorporate uncertainty into the model, please feel free to contact me, and I will be happy to respond and to answer your questions. Thank you for your attention, and I'll leave the references open.